Hello, my name is Paul, and this is my submission for CS50AI project Heredity, where we have used a Bayesian network model and inference by enumeration in order to calculate the joint probability of members of a family having either 0, 1, or 2 copies of a mutated gene, and also whether the likelihood of each person having a trait caused by the mutated gene or not. So for this project, we're given various family models um, and some information about the family, who are the parents of which children, and also in some cases we have knowledge of who has the trait or does not have the trait. So here we have a simple family with Harry, who's the child of Lily and James. We don't know Harry's trait status, but we know that James does have the trait and Lily doesn't have the trait. And so by essentially uh, creating every possible combination of person having 0, 1, 2 copy of the genes and also having the trait and not having the trait, and then calculating the joint probability of each combination and discarding any which violate the evidence that were given in the family data, we can calculate the overall probability for each person of them having 0, 1, or 2 copies of the gene, and also whether or not they would have the trait. So let's run our program for this first small family, family 0.csv, and we get these results. We can quickly do a sanity check. We know that Lily doesn't possess the trait, and see we get 100% chance of her not having the trait here, and similarly James does have the trait and we get 100% chance of him having the trait, so that makes sense. And we can do a quick sanity check here. So Harry is shown to have very low chance of having 2 copies of the gene, or just under 50% chance of having 1 copy, and are just over 50% chance of having 0 copies of the gene. So you know that Lily doesn't have the trait, and so because of this, she's got a high probability of having 0 copies of the gene. When you've got 0 copies of the gene, you have a very low chance of giving a copy of the gene to your child. So Harry has a very low chance of ever having 2 copies of the gene because it's very unlikely he'll get a copy from Lily. James, on the other hand, we know he does have the trait, and so he has around a 20% chance of having 2 copies of the gene and around a 50% chance of having 1 copy of the gene. Now, if James has 2 copies of the gene, he will nearly 100% give that a copy of the gene to Harry, and so Harry will have around a 20% chance of having 1 copy of the gene when James has 2 copies of the gene. When James has 1 copy of the gene, there's around a 50% chance of him giving his copy of the gene to Harry, and so that will give around a 25% chance of Harry getting 1 copy of the gene from James. So if you add the 20% chance from when he has 2 copies of the gene and the 25% chance from when he has 1 copy of the gene, we get around 45% chance, and that adds up here. So that does make sense. So we can quickly run through some of these more complicated family models, and we get various probabilities for 0, 1, 2 genes for each person and the true or false on the trait. For example, here, both Ron and Ginny, their parents are Molly and Arthur, and we don't know their gene status, their trait status. And as you would expect, if we look at Ron, who's got 0.1 and 0.88, that is identical to Ginny, which you would expect because they're both children of the same parents. And finally, let's run family2.csv. And I think this is a situation where you actually have a grandparent and parents, so there's a further inheritance there of the genes and whether or not they have the traits. So yeah, thank you very much for watching this, and see you on the next project.